Take a handful of dry sand and let it run through your fingers. It does what sand always does. It flows, it separates, it collapses the moment you release it. It has no structure, no integrity, no capacity to hold a shape or bear a load. It is, in every physical sense, the opposite of a building material. Now imagine that a magnetic field passes through that sand. In milliseconds, the grains stop flowing. They align. They pull toward each other and chain together, contact to contact, column to column, until the entire mass locks. The sand that ran through your fingers is now a rigid, load-bearing solid. Not because anything was added to it, not because it was heated or chemically treated, but because an invisible field passed through it and told it what to be. No cement, no heat, no chemical reaction. Turn the field off, the chains collapse, the sand flows again, the same grains, the same material. Loose, then solid, then loose again as many times as you need. This is magnetic granular jamming. It has been demonstrated in laboratories. It is in active development for surgical instruments that stiffen inside the human body on command. It is now inspiring early concepts for the Moon and Mars, where regolith is the only building material and cement is impossible. And it may represent the first genuinely reversible method of turning loose ground into solid structure, with implications for every eroding coastline, every earthquake zone, and every unstable foundation on Earth. So why isn't it everywhere? That question will take the length of this documentary to answer properly. The short version is that the physics arrived before the engineering. What researchers discovered was real, repeatable, and extraordinary. What came after, the particle design, the field geometry, the yield, stress, the scale, is still being worked out. But before we go deeper into how this works, there is something about this that changes everything. It is reversible, not partially, not under limited conditions, fully, instantly, completely reversible. Reverse the field and the alignment breaks, the chains collapse, the material flows, no residue, no chemical trace, no permanent alteration of any kind. We have always built with permanence as an assumption. A foundation is poured and it stays. Every construction method in human history has been a one-way process. You make the change persists. Magnetic granular jamming is the first construction-relevant material phenomenon that runs equally well in both directions. The same physics that builds the structure dissolves it. The same switch that turns sand into stone turns stone back into sand. Keep that in your mind, because every application that follows is not just a story about a material that becomes rigid. It is a story about a material that becomes rigid, and then, when you are done with it, returns to exactly what it was. That has never existed before. Granular materials are everywhere: sand, gravel, powder. They are collections of discrete solid particles that push against each other but do not bond. This is why sand flows like a liquid when loose, but can support weight when compressed. Physicists call the transition from flowing to rigid a jamming transition. Pack enough grains tightly enough and they lock against each other through friction and contact. The whole collection suddenly behaves like a solid. Conventional jamming requires mechanical pressure. You physically compress the material until it cannot flow. Now here is the thing that changes everything. What if the pressure came not from outside the material but from within it? What if the grains themselves could be made to pull toward each other without being touched, without being compressed, without anything being added? That is the question. And magnetism is the answer. If grains are magnetic, or coated with magnetic material, applying an external field does something remarkable. Each grain becomes a small magnet aligned with the field. Magnets aligned with the same field attract each other along the field lines. The grains pull toward each other in a directed, structured way, forming chains and columns aligned with the field, just as iron filings organize around a bar magnet. Those chains create what researchers call a force-bearing network, a web of grain-to-grain interactions spanning the entire material. In a loose system, forces die out quickly. There is no continuous path for stress to travel. In a jammed system, those paths exist. Stress applied anywhere travels through the grain network to the boundaries. The whole thing holds as a unit. Turn the field off, the attraction disappears, the network collapses, the grains are loose again. And all of this is still happening to something as simple as sand. Think about what that means. The same handful of sand that ran through your fingers, loose, structureless, becomes, under a magnetic field, a continuous load-bearing network. Not because it changed, because it was asked to. The energy required to maintain the jammed state is only the energy required to maintain the magnetic field. At the field strengths used in current laboratory systems, that cost is lower than the materials and labour cost of chemical alternatives, though its full characterisation at construction scale remains an open question. Every previous method of stabilising loose ground shares the same basic logic. Add something to it, drive steel piles, inject chemical grout, mix in cement. In every case, something is brought to the site, left there, and the ground is permanently changed. Magnetic granular jamming introduces nothing. It applies a field, the material responds, and when the field is removed, the material is identical to what it was before. This is not an incremental improvement on existing ground stabilisation. It is a different category of intervention. The comparison is not between two methods of doing the same thing. It is between doing something to the ground and asking the ground to do something itself. The question researchers faced once they understood this was not whether it was useful. It was obvious that it was useful. The question was whether the physics could be made to work reliably enough to be used. The research has roots in magnetorheological fluids, suspensions of magnetic particles in liquid that stiffen when a field is applied. By the early 2000s, magnetorheological fluid technology had reached commercial applications in automotive suspension systems and prosthetic knee joints. But magnetorheological fluids require a carrier liquid. The leap to dry granular materials required asking a fundamentally different question. Not how do magnetic particles behave in a fluid, but how do they behave when they are the structure itself? Researchers studying granular physics found that stress inside these materials is not distributed evenly. It concentrates in force chains, narrow pathways of highly loaded grains, while most particles carry little load. The rigidity of the entire system depends on those chains. Magnetic fields do not just jam the material, they organise those force chains deliberately, aligning them with the field direction and creating a structured internal architecture that mechanical jamming alone cannot produce. That insight opened a decade of work. The challenges that emerged explain why the technology is still developing rather than widely deployed. Particle design remains unresolved. Irregular particles create stronger mechanical interlocking, but particles optimized for magnetic response tend to be smooth and spherical. The better a particle responds to the field, the worse it jams mechanically. The better it jams, the worse it responds to the field. Field geometry is another challenge. A uniform field produces a uniform structure. But by shaping the field, researchers can create regions that are rigid and regions that remain soft. A material with programmable stiffness. This is not just a stronger material, it is a controllable one. But if this works, why hasn't anyone built with it yet? Consider what this means at the scale of a human body. In minimally invasive surgery, tools must bend to reach their target, and then become rigid to perform precise work. Traditional systems rely on pneumatic pressure and external lines. Granular jamming replaces that with magnetizable particles. With the field off, the tool is flexible. With the field on, it becomes rigid instantly. No external line is required. The same physics that controls a handful of sand can control a surgical instrument inside the human body. Now scale that up. Loose ground in earthquake zones can suddenly lose strength, collapsing structures built on top of it. Conventional stabilization methods are expensive, permanent, and often involve chemicals that remain in the ground. Magnetic granular jamming offers a reversible alternative. Apply a field and the ground stiffens. Remove it and the ground returns to its natural state. This allows temporary stabilization for construction, flood protection, or emergency response, without permanently altering the environment. But there are limits. At the scale of buildings, the strength of magnetically jammed materials is still significantly below structural concrete. That gap is the primary reason this technology is not yet used in construction. And yet, in environments where traditional materials are impossible, the equation changes. On the Moon or Mars, transporting building materials is prohibitively expensive. Both environments already contain granular material, regolith, that could be used if it can be controlled. The concept being explored is simple in principle. Process the regolith, apply magnetic fields, and form structures directly from the material already there. The challenges are real. Lower gravity changes how particles interact. The achievable strength is still limited. The engineering problems are not solved, but the idea remains compelling. Building without bringing materials from Earth. Which brings us back to the original question. Why isn't it everywhere? Because the strength is not yet high enough, because the particle design is not solved, because the engineering has not caught up to the physics. But the underlying principle works. A small number of force chains carry most of the load. Those chains can be controlled, and if they can be improved, the strength of the entire system increases. How far that can go is still unknown, and none of those unknowns have stopped the research. There is a reason we return to that handful of sand. For as long as we have built anything, we have changed materials permanently, firing, mixing, transforming them into something new. This is different. That same handful of sand you started with, the sand remains sand, but under a magnetic field it becomes something else. A structure, a solid, a material that holds, and when the field is removed it returns to exactly what it was. We are not making stone, we are making something more interesting. We are making matter that listens.